Welcome back to Bite-Sized Breakthroughs, everyone. Today we're diving into a research paper that tackles a crucial limitation of CLIP, the powerful vision language model. Joining me is Dr. Paige Turner, the lead researcher on this project, and Professor Wood Spectrum, an expert in multimodal AI. Paige, tell us what's the core problem that this paper addresses.
Thanks for having me, Alex. Essentially, CLIP, while incredibly versatile for tasks like zero-shot classification and text-to-image generation, has a rather short attention span when it comes to text. It's designed to handle a maximum of 77 tokens, but in practice, its effective length is even shorter, only around 20 tokens. This limits its ability to process detailed descriptions and understand complex image-text relationships.
So we're talking about a bottleneck in understanding rich and nuanced text. That's a major limitation, Paige. Professor Spectrum, can you expand on the implications of this issue for the field of multimodal AI?
Absolutely. This is a critical issue because it limits the scope of applications for CLIP. Consider tasks like text-based image editing or generating images from detailed prompts. Imagine describing the intricate details of a Renaissance painting, or instructing a model to create a scene with specific lighting effects and character interactions. CLIP, in its current form, just can't handle that level of complexity.
That's a great point, Professor Spectrum. Paige, how does your research, long CLIP, address this challenge? What are the core innovations you've introduced?
Long CLIP introduces two main strategies: knowledge-preserved stretching of positional embeddings and primary component matching during fine-tuning. The first one is about extending the effective text length without disrupting the existing well-trained representations of shorter text. We found that the first 20 positional embeddings are well-trained, so we keep those intact and interpolate the remaining positions with a larger ratio, effectively allowing the model to process up to 248 tokens. It's like teaching it to understand longer sentences without forgetting what it already knows about shorter ones.
So it's a clever way to train the model to handle both short and long texts without losing the existing knowledge. Very interesting, Paige. And what about the primary component matching? That seems equally important.
Yes, that's where we address the issue of understanding complex relationships between attributes within an image. During fine-tuning, we align both coarse-grained and fine-grained image features with short and long captions, respectively. It's like teaching the model to see the big picture, the key attributes of an image, as well as the finer details. This helps it learn to distinguish the relative importance of different elements in a scene, which is crucial for understanding more complex descriptions.
That's a really elegant approach, Paige. Professor Spectrum, how does this methodology compare to existing methods for increasing context length in language models?
Previous approaches, like simply interpolating positional embeddings with a fixed ratio, often involve a trade-off. They might extend the length, but can disrupt the model's ability to represent shorter texts effectively. Long CLIP's knowledge-preserved stretching addresses this issue by intelligently retaining the well-trained lower positions while extending the upper positions. This is crucial for maintaining the model's accuracy on a wide range of tasks.
So it's about being mindful of the existing knowledge base. Professor Spectrum, have you seen any other research that focuses on understanding the relationships between attributes in multimodal AI?
There's been some work, Alex, but it's often limited to aligning text phrases with specific image regions. Long CLIP takes a more holistic approach by aligning both coarse-grained and fine-grained features, essentially teaching the model to understand the global context alongside the details. This is a more sophisticated way of capturing those complex interactions.
That's a key distinction, Professor Spectrum. Paige, let's dive into your experiments. What kind of data sets did you use, and what were your key findings?
We evaluated long CLIP across 3 tasks: zero-shot image classification, short caption image text retrieval, and long caption image text retrieval. For training, we used the shared GPT-4V dataset, which contains 1 million image-long caption pairs. Our results were quite encouraging. On the long caption retrieval task, using a custom dataset called Urban 200, containing images and detailed descriptions of urban scenes, long CLIP showed a 25% improvement in recall rate compared to the original CLIP. We also achieved a 6% improvement in recall rate on short caption retrieval tasks using the COCO 2017 and Flickr 30K datasets. Importantly, LongClip maintained its zero-shot classification performance.
So not only did it improve performance on long text tasks, but it also didn't negatively impact its ability to handle short texts. That's a significant achievement, Paige. Professor Spectrum, what are your thoughts on the experimental setup and the implications of these results?
The use of both short and long captions in the training process is a crucial element of their success. It allows the model to learn to prioritize important attributes while still capturing detailed information. These improvements in retrieval performance are very promising, especially for tasks like text-based image search and image-based text retrieval, where understanding nuanced descriptions is key.
It's not just about retrieval, though, Paige. You also demonstrated the plug-and-play nature of LongClip, which is quite exciting.
Exactly. Since we've preserved the clip latent space, LongClip can be directly integrated into various downstream applications, such as image generation models like Stable Diffusion. We replaced the original clip text encoder with our LongClip encoder, and without any additional training, we were able to generate images from detailed prompts that were previously beyond the capabilities of clip.
That's remarkable, Paige. So, it's not just about improving retrieval tasks, but also enabling new capabilities in image generation. Professor Spectrum, what does this mean for the future of these kinds of image generation models?
This is a huge step forward, Alex. It opens the door to generating more realistic and detailed images, capturing specific attributes, relationships, and even artistic styles based on complex descriptions. Imagine a future where artists can use text prompts to create intricate works of art, or designers can generate highly personalized products based on detailed specifications. LongClip could be a game changer in these areas.
That's a compelling vision, Professor Spectrum. Paige, what are the limitations of LongClip, and what are the next steps in this research?
While we've significantly extended the text length, LongClip still has an upper bound. We're exploring relative positional embeddings, which could potentially remove this limit altogether. We also need to further evaluate LongClip on other vision language tasks, such as question answering and image captioning. And of course, we want to investigate the potential of training LongClip on even larger and more diverse data sets, which could unlock even greater capabilities.
Those are exciting directions, Paige. Professor Spectrum, what are your final thoughts on LongClip's impact and future potential?
LongClip represents a significant leap forward in vision language modeling. It's not just about extending the capabilities of clip, it's about bridging the gap between human understanding and machine perception. This research opens up a world of possibilities, from creating more realistic and engaging content to developing AI systems that can interact with the world in a more nuanced and sophisticated way. I believe this is just the beginning of a very exciting journey.
That's a fantastic way to put it, Professor Spectrum. Paige, thank you for sharing your insights on this breakthrough research. And to our listeners, we hope you've gained a deeper understanding of LongClip's potential to revolutionize how we interact with images and text.
Thank you, Alex. And thank you, Professor Spectrum, for the insightful discussion. It's been a pleasure.
The pleasure was all ours, Paige. And to our listeners, stay tuned for more bite-sized breakthroughs in the world of AI. Until next time, keep exploring and keep learning.